Welcome to a presentation by Exact Education. This video will explain the operation of a passive low-pass RC filter circuit that has been built up on the Loctronics modular component system. We have a signal generator providing us a sine wave of 500 Hz, 5 volts peak to peak. We have digital oscilloscope so that we can see the waveforms and we can measure amplitudes and phase shift. We also have a digital multimeter which doesn't display waveforms but gives us a RMS value of the voltage coming out, root mean square, which is the power content of our AC signal coming out across the capacitor here. So we have 180 ohms connected in series with a 2.2 microfarad capacitor. Our theory tells us that we have a voltage divider circuit whereby we expect a voltage coming out of 2.51 volts peak with a 500 Hz 8 volts peak to peak or 4 volts peak signal going in. We have a voltage divider determined by the impedance of the capacitor divided by the impedance of the whole circuit. Impedance of the capacitor is 144.7, impedance of the circuit is 230.9, 144.7 divided by 230.9 multiplied by our 4 volts peak circuit signal going in gives us an expected voltage coming out of 2.51 volts with a phase shift of 51.2. In a previous video we simulated the circuit, and in the virtual world we had voltage and phase shift coming out to be very exact to those expected figures of 2.51 volts peak and 51.2 degrees phase shift. What we'll now do is we want to measure the amplitude of channel 2. So what we have coming out is we have a 5.0 volt peak to peak amplitude coming out, which gives us a 2.50 volt peak value coming out, which matches very closely against our 2.51's expected. So that's very close to the expected figure. What we want also to do is to examine the phase shift between these two waveforms using the digital oscilloscope. So what we'll do is move the multimeter to the side, we'll wind down the horizontal time base, we will use these cursors to measure the time difference between where the waveforms cross the zero axis. So we have a reference and we'll move this one here to where it crosses the zero axis. It's obviously your eyesight comes into play in the resolution of the screen. I would say it's, move that one, yeah, there. I would say we've got a figure of 280 microseconds time difference to where they cross the zero axis. So our 280 microseconds divided by our 2000 microsecond cycle time as a fraction. We do 280 divided by 2000 to give us a fraction of 0.14. If we multiply by 360, that gives us a phase shift of 50.4 degrees. That 50.4 degrees is a little bit lower than the expectation of 51.2, but it is well within reason in terms of we're measuring in a physical circuit. So we don't necessarily know this digital scope has been calibrated. We don't necessarily know whether our digital multimeter has been calibrated either. What we expect out of our multimeter is a root mean square value. That root mean square or RMS value is the power content of an AC signal. If we have 2.51 volts peak going in, if we divide that by the square root of 2, we would expect an RMS voltage to be measured on a multimeter of 1.77 volts. So what we could see is this meter appears to be reading a bit lower by about 0.1 volts. If we want to validate our meters, our readings using different meters, what we could do is, instead of reading from a digital multimeter, what we will do is we will use an AVO and we will read a voltage from our AVO meter. So if we put our AVO meter onto the 30 volt range, we can see that we are reading yes, it's difficult to be accurate on an analog meter. You're analysing the position of a pointer on top of a printed scale. So there's obviously more operator skill involved with an analog meter, and we're reading just over 1 volt, but it's difficult to tell accurately. If we try and we'll move the time base back up to see the whole signals. One of the interesting things with an analog meter, as you can see on the screen, is there's more manual intervention with an analog meter because you've got to manually set the ranges. If we turn the range down to read more accurately on the AVO screen, what we can see is if we turn the scale down too far, we can see the amplitude of V out coming out being reduced. Why would that happen if we use the smallest scale on the AVO meter? Well, the answer is that when we turn the scales down on the AVO meter to on the 3 volt scale, the lowest one we can get, the input impedance of this meter is clearly going down substantially, and it's affecting the voltage coming out because it's loading it up too much. So at that 3 volt scale, the impedance of this meter is not high enough to give us an accurate result. The impedance of this meter is somewhere akin to the impedance of the capacitor. So it's only on the higher ranges we can actually measure more accurately, but it is very difficult to gauge accurately a reading, which this one is reading just over, it's actually reading below, it's reading between 1 and 1.5 volts RMS on our AVO meter. Take our AVO meter out and put our digital one back in. We want to be seeing that we're back to reading that value again, 1.66. So why would our readings in the physical world be different to the theory in the virtual world? Well, a number of reasons. Our resistor may not be exactly 180 ohms. Our capacitor may not be exactly 2.2 microfarads. In the virtual world, the SPICE models will use exact values. We don't know how accurately this is reading. We don't know how accurately this is reading because we don't have the calibration certificates to hand. We do know what we've demonstrated from the analog meter is the importance of input impedance of meters, and we can demonstrate that here with the analog meter. If we measure the input impedance, of our analog meter, we can see that on that particular range there, 30 volts, that particular range there, 30 volts, the input impedance of that particular meter is 61 kilo ohms. which is much higher than the impedance of across the capacitor, so we do get a fairly accurate voltage out measured. If we put the scale down a bit, we can see that the input impedance goes down to 10k. If we put it onto the bottom range, we can see our input impedance goes below 2k, it goes down as low as 300 kilo ohms. Now that 300 kilo ohms is far too small input impedance, and it's now not giving you an accurate voltage coming out because the input impedance of the AVO meter is too low.